For our main presentation today, we have a presentation by Al, N680T, on solar energy, and very important topic these days, especially field day coming up, not to mention the power outages we seem to be having up here in the foothills. So with that, Al, if you're around, share your screen, open up your mic, and take it away.
I'm Al, N680T, and a little bit about my background. My solar experience mainly is from work and home and amateur radio. During my working career, we had solar systems that powered mountaintop repeaters. In some cases, the only power available was a solar battery. And one of those sites is up near Lake Tahoe. It's called Scout Peak, and it's got probably a 12 or 15 kilowatt solar array with battery backup, and it does have some generator support, but it's limited. It's mainly a solar site. So we did maintenance on those panels and on the solar equipment that was internal. And later on, I did solar systems on mountaintop sites in St. Helena and Atlas Peak. And we had some limited solar sites there. Amateur radio wise, I've used solar power for more than 20 years, mainly at field day locations. And let's talk a little bit about portable solar systems for amateur radio use. Generally, you're going to be running a 100-watt sideband radio, or maybe a VHF FM radio or digital, in which case you don't need a great deal of solar power. Generally, it's a battery regulator and panel. And the panels I originally used were 40 watts. They were made by a company called Unis Solar, and they were fairly small panels, maybe about 2.5 feet wide, 3 high, and they were very inefficient, and used a kind of a PVC mount system. Basically making up a couple of PVC unions and legs, and open up the, attach the legs at the top, use a couple of 90 degrees and a bottom piece, and you have an adjustable, lightweight solar stand for the panels. So that worked out well for and we just paralleled a bunch of those. If we, depending on how many stations we were running, generally we ran about maybe 120 watts or 140 watts of panel, and just kind of moved them around location wise, and used a 50 or 60 amp hour battery. And back in those days, I don't think they even had gel cells. We were using lead acids, and batteries are another topic, and we'll talk about those a little bit, because you can't have a solar system without especially in the field, without some sort of battery power. So the other sorts of solar are portable solar systems, or RV, of course. And generally speaking, on the RVs, you're going to run more than 100-watt panels. In the case of one of my friends, Sal K6SAL, who's a member of this radio group, has, I think, almost a kilowatt on his 40-foot RV, or maybe more, maybe 1,200 watts, and a couple kilowatt inverter, sine wave inverter, and he's running, I believe, 300 or 400 amp hours of lithium-ion battery. And we'll talk a little bit about that type of battery versus lead acid or AGM gel batteries. And what the advantages are on those. Typically, the batteries I recommend today, if you're going to run any kind of portable operation, are either AGM, the gel battery, and they're a little bit less expensive. They're more, of course, than a lead acid, but they don't discharge sitting around as much. Typically, a lead acid could lose as much as 10% a month of its or more of its charge capability just sitting. AGMs typically 2, 3, 4% a month. So they're much better for discharge sitting. And best of all, of course, lithium ion phosphate. Those things can run many, many months and not even lose a few percent of their charge. And advantage for those, weight and capacity. The lead acids and AGMs are heavy. And you can only get about 50% of the rated capacity. So if they're 50 amp hour, you're lucky to get 25 amp hours out of them. Whereas with a lithium ion, if they're rated at 25 or 30 amp hours, you can fully discharge them, and the battery monitor system internal to the battery will shut them down. So that's off topic for solar panels, but solar panels, by the way, are photovoltaic panels, and they're basically silicon wafers, and they're arranged in series parallel groupings to get more voltage and more current. So panels typically are just composites of a bunch of these things. The three types of panels that basically we have are called monocrystalline, polycrystalline, and thin film. Those are the most prevalent panels there are. There are one or two other types, like the shingle panels, if you will. They can be a combination of both the flexible solar or monocrystallines. But typically, those are the three that we're going to see. The ones that we see the most of in commercial use are polycrystalline panels. And I think I shared some of those. I'll bring that up again here in a second. First off, we'll just look at a little bit of the racking. Let's see if I can get that up. There we go. So what you're looking at now is rooftop mount for these are polycrystalline panels, and generally they're 72 cell panels. Generally, you're going to have 60 cell or 72 cell for the commercial operations or residential stuff. For smaller applications, and these panels generally run open circuit voltages around 40 volts, between 32 and 40 volts, and ampere outputs accordingly. These are 315 watt panels, and I've got 14 of them up here. So as what you can see right now is the racking system up, and the panels just starting to get mounted. So when you're putting a system like this together, I had the system. I engineered this system, and a buddy of mine drew up the drawings for me. I had to submit my information to SMUD, the local utility district, and then get a permit, submit the plans and the drawings to the building department. So all of that being said and done, I spent about $350, $400 for the permitting. The most expensive part of this job was really the roof mounts and the racking system. The roof mounts, I have a PVC roof. This is on my home, by the way. And that roof required special booting and welding of the mounts. And I used very high quality mounting system. There are lots of different mounts. The ones that I use are called Iron Ridge Solar. And if you go and look at their stuff, it is typically really high quality. They have mounting systems for shingle roofs, for flat roofs, and tile, and you name it. And they use an extruded aluminum rail. And there's another picture here of the railing coming up. So there's the rails. And I've got my rails set up on, if you look at the anchors, they're two different heights. So that's how I get my elevation and tilt for the panels. And the tilt is roughly our latitude minus about 10 degrees. So if you look at your latitude and take away 8 to 10 degrees, you'll have a pretty good angle for the spring, summer, fall angle to the sun. My particular direction for the roof is almost 180 degrees magnetic, which is perfect. And I don't have any obstructions in terms of anything across the street, so I get direct sunlight.
Question, Al.
Yes.
When you determine your angle, do you set that for winter angle or a annual average?
It's an annual average, that latitude -8 or 10, 12 degrees. You can do a little bit of research, but that turns out to be a pretty fair average. Ideally, you'd want to be able to adjust the tilt angle on those panels to optimize the output. And I'll talk a little bit about that down the road. But as I said, these panels, the good thing about these panels, and for most commercial applications, the larger the panel you can put up there, the better. And my particular application, I was able to get these panels at a very reasonable price. They were commercial panels that were installed and put in by a professional solar company. And after they got them installed, they found out they were the wrong panels. So they had installed, I think, 200 or 300 of them. So they couldn't sell them as new. They had to sell them as used, and they were heavily discounted. So it worked out well for me. And not so much for them. They had to eat the cost of whatever they lost on the panels. But so here you see the panels are in. The install there is completed, and the fellow that's up there helping me is W6AW, Bob, another amateur radio operator. So as far as anything I had for help, I had help getting the racking system and the panels put in. The mounts I had done commercially by the roofer. I did the racking and everything else. Bob helped me lift the panels up there and get everything bolted down. Another slide here for that. And the ladder was just partly the story. I had a man lift as well. So I brought the panels up here with a man lift. But let me talk a little bit more about, here's a backside view of the panels. And if you look closely, you'll see a module mounted to the rail. That module is a micro inverter. So we'll talk about those just a bit. Okay, so types of inverters and types of systems. My system and most systems on the residential houses are what they call grid tie systems. So they actually take the that's produced by the panels, convert them from DC. The panels are DC, so they convert the DC to AC. And generally they do that either right at the panel or down with a central box. So if you do it at the panel, it's with a device called a micro inverter. The micro inverter, and I'll show you one right here. I've got one in hand. This is a micro inverter. And if you look at it, it's got a nice heat sink. It's got some mounting tabs on the bottom that fit into the rails or the panels. Some additional tabs and mounts on top. If you look at the back side, it's just more heat sink. And you can see the wires coming out of it here. Now the type of connector, the DC connectors are those two top ones with the ends on them here. Those are called MC4 connectors. And that tends to be the industry standard for most solar today, the MC4. There's lots of different, there are other connectors that are used on solar panels, but these tend to be the most common. And then, so the DC feeds into this thing. It optimizes when the inverter starts, how long it runs, and how it produces power. So they're individually optimized.
Al, is that case plastic or metal?
The case is solid metal, and it's aluminum. It's built on aluminum. Now this particular inverter is rated close to 300 watts. It's 293 watts. So that being said, if you're running a panel like my 300 watt panels would not overdrive this inverter. The 300 watts is optimum. That's at maximum sun, maximum radiation. It's almost impossible that you're ever going to get that much sun or have the angle just right to get that much power out of them. So this inverter rated at 293 watts is way more than you need. The standard manufacturers for these inverters, there's a company called Enphase, and that's one of the biggest manufacturers of all the micros. And Enphase makes, they start at about 160 watts and they go up to about 260 or 280. But 260 inverter will run fine on a 300 watt panel. It sounds like you're a little bit of an oxymoron, but you'll never really get that much power out of the panel. So the MC4 connectors plug into the panel, and outside of the inverter, you have an AC plug that actually plugs into a bus, if you will. So you got a cable that's quite long, and it has a number of connectors on it. Say you're going to run 10 panels. So you order the AC cable that is basically the feed that has 10 plugs, 10 outlets. So each inverter will plug into that string, and that end of that string feeds your main AC down to the box. So back to, let me share, go back to sharing here for just a second. Might take me a moment. Well, I'll share in a minute, but let's talk about what the AC connection is. Basically, that inverter takes DC voltage from the panel, converts it to 220 single phase AC. And that as the panel comes up and that AC voltage feeds down, it basically feeds right into your power box. And it does that via another circuit breaker in a box called a combiner, a disconnect, and then from the disconnect, it goes into your main circuit breaker panel and feeds right into one of the breakers. So you put a breaker in for your solar, and in essence, you backfeed. So that inverter is actually feeding the line. And the way it does that is it senses the phase and the voltage from the connection to the commercial mains, and it syncs the inverter up automatically. So as the sun comes up, the DC voltage comes up, and it's enough to get the inverters, microinverters started. They start individually outputting their power. And if it's times one panel or times 10, they're additive. So if you have 10 300 watters, you have potentially 3,000 watts of power headed down to your main panel. All those inverters sync to each other. So internal to the microinverter is a computer, and it phase senses the 220 volts. It senses every other inverter in line, and it ultimately, it also has its own Wi-Fi connection to feed a monitoring circuit. So it feeds down to a controller, if you will, and that controller can look at each and every inverter as it outputs a signal and power, and tell you what the power is, what the voltage is, what the temperature is, everything. Generally, those things are set up so they network into Wi-Fi. They tie into your system Wi-Fi. They go out to the manufacturer in some case. Like my particular inverters are made by a company called ABB Power One, and my controller ties into their network, and I have a free service that shows me the total power output of each and every inverter and my instantaneous power at any one moment in time. So
Al, just a quick question.
Yes.
With Elon Musk announcing that every new system that he installs will be with a power bank, do you think that will change away from having the inverter mounted on each power or on each panel and then going through a double conversion? Or do you see that changing the industry with that announcement?
No, what he's talking about there is that particular system is a battery. It's called a hybrid system. The DC panel output is still having to go to AC one way or the other. Unless you're running a standalone system and you're charging your own batteries and your house is running off DC, you're going to have conversion from DC to AC on any solar system. On the grid tie systems, you feed the energy back to the grid. So it goes back to PG&E or SMUD or whoever you've got. If you make more than you're using, the meter it actually has 2 meters. The smart meter they will install goes backwards. So if you're making more power than you use, they pay you X amount of cents per kilowatt hour. And I'll talk about that a bit later. Let me just continue with the technical part of this. If you got any questions, just kind of put them in the end. But the Elon Musk Powerwall system is different. You're really getting lithium ion batteries and you're storing some energy. You're both feeding the grid and you're storing some energy in the batteries during the day when you have solar output. At night, it switches to where those batteries are supplying a hybrid converter, if you will. Instead of having a single micro inverter, you now have another. You have one inverter on the wall, and you're feeding DC from the panels right to that single inverter, not micros. And now, at night, the batteries feed that inverter instead of the panels, and you get energy as long as the batteries have energy. So typically, those things are, I think they're 5 kilowatt hour batteries, and you get different banks. You can get 10, 15, 20 kilowatts of battery. Presently, the batteries are outrageous. So I wouldn't even consider having one of those things. And 5 kilowatts or 5 kilowatt hours of power, that's fine for for lighting and minor usage, but if you turn your air conditioner on even for an hour, you'd be out of juice in a hurry. So let me continue on here, and then if you have any questions, just pick them up at the end. But let's talk about the types of inverters again. First off, I just told you about micros. Secondly, you have a standalone inverter. The panels now get put together so that the voltage output of the panels is in series and it's DC. So if you're taking a panel voltage out that's 35 volts times 10 panels, you have 350 volts DC, and you're running DC down the conduit to an inverter that's bolted on the wall somewhere or outside, inside, whatever. It takes that 350 volts DC from the panels and converts it to 220 volt single phase AC that feeds the power grid. Same way as the micros, except now you have a single point of failure. Micro quits, one micro inverter quits, and you have 14 panels, you now have 13 panels. It just takes care of itself, and you drop one micro. If you drop the main inverter and that happens, you lose the whole system. That being said, these new micro inverters, both micros and the standalone inverters are what they call maximum power point transfer. And what they do is they optimize the output of each and every panel. So there's 3 ways of doing that. Right now, you can do it with a micro inverter, you can do it with a smart single inverter, or you can do it with what they call an optimizer. And the optimizers basically go on the series string panels that have high voltage. So instead of if you shaded one of those panels and they're in series, you're going to lose almost all your power. But if you shade a single panel that's in a series string, the parallel microinverters don't have that problem, because if you shade one panel, you still have all the rest of them working. They're parallel. But the series string panels have issues, and to correct the issues, you use a single device to enhance the panels. And Any rate, that's the way that those things are set up. Let's see here. I talked about the design for the systems, the permitting, racking, roofing, microinverters. Basically, my neighbor got a system installed like mine. They had it done by a local installer. Cost him $26,000 for this first, a little bit smaller system. My system, engineered and installed, was $12,000, and I got $3,000 back from the feds. So I put in a 4.2 kilowatt system, and the cost was about $9,000. And my neighbor did one a little bit smaller, it was $27,000. So big difference in cost. And I use top quality stuff, and I'm sure whoever put theirs in didn't. What I would tell you is that if you don't even think about getting one of these systems installed by the companies, Home Depot or wherever they're trying to sell you solar, because the only person that makes money on those sorts of issues, no matter how they do it, is the company. It's not, they're not doing it for your benefit. You won't even come close to getting your money back. Now, if you want to do a system, there are companies out there that you can get online and do some wholesale solar sites. Just look for wholesale solar. There's 2 or 3 of them that will offer complete systems. They will actually do the design. You send them your address. They can figure out where your house is, what it looks like. They can do design. They can do complete layout, and they can sell you a package with panels and single inverters or micros. And it's probably less than half of what one of these other outfits would want to charge you. And you can get a local installer that just says solar install. That you don't have to be one of these large companies to be able to do it. They will ship the panels, the equipment, and everything else right to your location. So there's lots of ways of doing this and making it cost effective. Let me see here. We talked about how many inverters. Panel efficiency, monocrystalline, polycrystalline, and thin film. And the monocrystalline panels are about 18% efficient, which, you might say, that sounds pretty horrible. But what we're talking about is solar energy transferred to power. So input power versus output energy. Monocrystalline tends to be the highest efficiency in it. It's about 20% if you're lucky. Polycrystalline, a few percent less. And the thin film, which is foldable, folding panels, etc., are the worst. They're about 11% efficient. Cost-wise, the larger panels are more they're more cost effective. So if you get a larger panel, you're going to pay less and you get more energy. How long do they last? Typically, they're going to be rated for at least 15 years, 10 to 15 years, and no less than 70% of full rated power at the end of that time. And I would tell you that it's more like 20 years. So if you buy some older panels and you're going to use them for your own purposes, chances are you're going to do just fine. And able to check them, take a look at the voltage and take a look at, use some sort of a load. We talked about loads. I give you more information about how to do that if you're truly interested, but voltmeter and resistive wire works really well. Let's see, what else? Time-wise, I think we're getting right close to the end of my time. So charge controllers, I'm going to show you a few. This is one that I'm going to install in an RV. I'm going to put about 900 watts in my RV. And let me see if I can get this right to where you can read it. Oops. I don't know if you can read that or not. But at any rate, this is it's called a Solar Smart Charger. It's MPPT, which is the maximum power point transfer. It's rated at 50 amps out. So we'll take about as maximum of about 100 volts in from the panels, and we'll output up to 50 amps. So if I got a kilowatt of panels on the roof, and I'm lucky and I get about 800 watts out of them, that would, at 12 volts, 50 amps is going to be close to 50 amps at 10 volts is 500 watts. So, 50 amps at 12 volts, 600 watts. So this charge controller would do it. So I'm going to input the output of the input of the panels will feed this, and the output of this will feed my lithium ion batteries. I put in 300 amp hours of lithium ion on my RV, and that replaced some monster lead acids. The lithium ions weigh, I think, about the total weight of all three batteries is less than 60 or 70 pounds. And they replaced golf cart 6-volt flooded batteries that weighed about 90 pounds apiece. I had 6 of those. So 540 pounds. I changed it out with about 70 or 80 of lithium batteries that output more power. Of course, the cost of those batteries is high. It's coming down, but it's still right now very high. Also, I have on my RV, on this charger, this smart controller is full Bluetooth interface. So app on the phone, I can tell exactly what's happening with the charge, how much power I'm pulling out of the batteries, how much I'm putting back into them, how much is left.
Do you have to load balance your batteries with this type of charging?
Yes. Now, that being said, each battery has a BMS built into it.
Okay.
I'm running Battleborn 100 amp hour batteries, and they have built into the lithium ion batteries a charge controller or battery management system that equalizes each cell. So very important on lithiums that the cells are very closely charged voltage wise. So the BMS internally will do that. These most of the lithium batteries you get today have their own internal battery management system, and normal charging voltage from your alternator or whatever source is just fine. They'll take that and they'll make the appropriate changes so that the internals on that battery are happy. That's one type of controller. Here's another 20 amp charge controller for smaller panel. So this is I think this is about a $40 or $50 charge controller, and this is a Bluetooth interface module that plugs right into it. Also, you also have an app so you can tell what's happening. This would be perfect for your field day setup. So 12 volts, 20 amps, 240 watts, basically. So the energy you would get, say you put up 120 watt panel for your field day use. That panel, if it's doing what absolute maximum output is about 10 amps. Typical solar day, you're going to get, say, 6 or 7 amps out of that panel times 6 hours. So you'll get 42 amp hours in a solar day out of that one panel and a charge controller like this.
What's the make and manufacturer of that, the model of that device?
This one is called Renogy, RENOGY. Amazon has them for $39 or $40, and the Bluetooth module I think plugs right into it. It's another $20.
Are those pretty RFI neutral?
When you're here, that's another subject entirely, and we'll talk about that just briefly. I know we're running out of time. So the RFI on solar systems, how does it happen and why does it happen? Well, first off, you've got a fair amount of current, and that DC voltage and current are being fed into an inverter that basically is an oscillator. They're typically high frequency converters, so they're running at, say, 20 to 200 kilohertz, and They take that signal and they run it into a sine wave inverter that's built internal to the device on the micros or the single inverter. So you've got an oscillator, you've got a power supply that's running at some frequency, and you've got DC wires feeding that. Now the shielding on those things, they're supposed to be manufactured so that they're shielded. So if you look at this guy again, it's pretty well encased. What's not encased are the wires coming out of it. So these DC wires are typically, now to get to, to get 300 watts and you got say 32 volts, you're going to be up near 8 or 9 amps feeding this. So if you couple long wires onto this thing, and you're, depending on the filtering, the internal filtering on the unit, you could generate some AC hash and some RF. And the longer the wires and the more sloppy the thing is put in, the greater chance that's going to happen. There's the best way to filter that stuff out. First off, if you buy quality equipment and you do good install and you got your wires short and paralleled, and you can minimize everything by making sure the ground to the racking system is solid, the ground to the micros is solid, and minimizing the length of the wires running from the panels to the micros. On top of that, our old buddy ferrite cores are the trick. Palomar Engineering, if you go to Palomar Engineering's website, they have several pages dedicated to eliminating RFI from solar systems. And there's two ways you do it. One, you either do it at the source, which would be the inverters, the panels, and the associated wiring, or you do it at the equipment. And you're looking for getting rid of common mode interference. So the clip-on ferrites work really well for on both sides, and then the actual cores work better on the DC wires, where you actually take several wraps through a core. So Palomar offers those for any solar system. That being said, they're not cheap. So you can wind up spending $70, $80 a panel to put on maximum interference protection per panel. Do you need it? Maybe. Okay. And I say maybe, depends on the inverter manufacturer and how well you do the install. On my system, I'm using solid aluminum mounting. So the mounting system I'm using is built by Iron Ridge Solar. And here's what it looks like. And it's extruded aluminum, and it's actually fits together and it bolts. And then on top of that, it's got grounding lugs that go on it. And then the panels actually have little brackets that slide into the top of the mount. So the mount has got a machined groove on one end. On the other end is another machined groove in the side, and the attaching pieces go right into it. So it's actually an engineered system. This stuff is strong enough to where it's rated for hurricane force winds at over 120 miles an hour. You can take a 1 or 2 foot section of this and drive a truck over it. You put 3,000 or 4,000 pounds on it and it won't bend. So it's a really super system. That's the one that you actually mount on a stand-up rail. Here's the same company. This mounts under a shingle. So what you do is you slide this piece under the shingle, and then there's this piece is the attaching. Now there's also a lever that goes, or a piece that goes on this, so you can extend it. So this is the type that you would use for an asphaltic shingle. MC4 connectors. So this is a single MC4 to 4. So there's ways to parallel the panels if you want to do add voltage or add parallel panels. You can do them with pre-manufactured connectors. All right, it is 20 minutes to 10. I think I better call it quits. Anybody has any questions? Yeah, go ahead with them and I'll try and answer them.
Yeah, Al, this is Greg. When you're doing the single inverter, can't you do a series parallel grid of panels to avoid the shadowing problem?
Yes and no. I mean, you can do, the best way to do it is with a single isolator device that goes on each panel. They call them enhancers. And, you know, they basically will look at each panel output and optimizer, excuse me. The word is optimizer. And they're an item that you can actually buy for each panel. And that's the best way to do them. As far as doing them series parallel, yes, you can do them that way. But if you use optimizers, you can put the panels on any which way you want. They could be facing north, south, east, west, and it will literally optimize each and every panel. So that's the most effective way to do it. And that's how industry does it typically.
Okay, thank you.
Any other questions?
I do know that Solar City got in trouble with their optimizers. That was, they received an FCC desist order on those. Is this a common problem with the optimizer units, or was that their particular?
It does happen more frequently with the optimizer units. The companies that build these things are not necessarily the best. They're buying them. A lot of them now are coming from China, and the FCC requirements for interference doesn't necessarily mean much to those folks. So I would tell you that if you buy them, be careful about who you get them from. You buy them from a reputable solar company, and likely they're going to be good ones. You get what you pay for. If you buy a cheapie from Alibaba, it might not be too good.
Yeah. Okay, thanks.
Anything else?
Brian, back to you.